Thank you. Thank you for the introduction. My name is Taesoo Kim. I have a multiple hat. I'm full-time at Microsoft as a VP in security research, and also I'm professor at Georgia Tech. Today, I'm going to talk about DARPA AIxCC and our approach as a Team Atlanta who won those competitions overall. I have various background in system security. We are specialized in finding vulnerability. We also write exploitation against. We also do tons of systems related security issue, but thanks to recent evolutions in AI, most of our research is now geared toward how to leverage LLM. For example, even doing symbolic executions, how to leverage LLM in a way that we can augment the LLM process by using LLM as one of the core components of those static analysis. Even for reverse engineering and writing exploitations, now LLM become very important role to solve some of the impossible problems that we previously encountered in those process. Said that, we are pretty much grounded. We won several of competitions, including Point2On and DEFCON CTF, which is Olympics of CTF players. But today I'm going to talk about DARPA AIxCC, which is one of, I'll say, once in like one of the biggest challenges in history in computer science, how to leverage LLM in a way to find and fix those vulnerability. Said that, I'm not AI person by training, but we knew how it works in general. But one of the key takeout of this message and talk is that how a security expert leverage LLM in a way to solve this domain-specific problem, or another way to say it, after we spending these tens of billions of tokens in this commodity LLM services, what are the lessons out of it? DARPA has been organizing such grand challenges several decades. Every 5 to 10 years, they've been organizing a grand challenge to address some societal problem. Self-driving car challenge 20 years ago is pretty popular among all these people. And then there was a challenge to design humanoid robotics for the rescue missions. And 10 years ago, there was challenges called Cyber Grand Challenge. Basically, the idea here is we're going to put a machine in a way to replace a human hacker, so that machine can now understand the binary and actually solve the security challenges by itself by creating exploitation. After several years of those challenges, they spark huge industry. For example, now it's common to see self-driving car on the road. There's a race going on in humanoid robotics right now. Immediately after DARPA CGC, we now see the wide adoptions in techniques like fudging in all over the places. DARPA AIxCC was announced in August 2023. There was a time that there was no particular interest in the GPT model at the time. But DARPA announced that what are the frontier capability of those models in a way that when we leverage those AI deeply in our security tasks, which I'm going to talk about today. But one of the goals of DARPA AIxCC is to design an autonomous system that automatically find and fix those vulnerability given huge pile of source code such as Linux kernel. And also, we are not talking about small scale toy program in academia as a benchmark. We are talking about the open source real software such as the Linux kernel and Nginx that really back the cyber infrastructures of the United States. And then as part of these competitions, they injected many of one-day vulnerability to the latest repository, and also they create synthetic benchmark in a way that they can evaluate the reasoning capability of those systems as well. But after these competitions, all the code bases and data is already being released as open source so that any other people can take advantage of them after. When we say bug, it's a very serious vulnerability in software. For example, these are the bugs that have some money assigned to it as part of the bug bounty. For example, if you find a bug in Apple product, they give out about $1 million depending on the product and how you actually demonstrate them. This is not just interested in academia, it's interested by whole organizations and community, including Microsoft and OpenAI and Google, who actually provide the foundation model to the competitions as well. During the competition, we have access to all these latest model with the high tiers throughput in a way that we can leverage those frontier model at the moment to find and fix those vulnerability. But we are not constrained by those AI model. We have option to create our own model, as well as we have a freedom to select which model that work for the best. Immediately after the competition was announced, there was semi-final competition happened a year before, and the final happened the last August. And interestingly, the amount of prize they assigned to each round of competitions, that after the semi-final, all the winning team of the semi-final got about $2 million as a prize. And for the winning team of the final, we got about $4 million as a prize. What's interesting here is that during the semi-final, about 42 teams competed on the stage, and only 17 proceed to the final. What's interesting here is that because it's open competitions, all these folks all around the world competed in this competition. Some PL-focused groups also participated, and security folks also participated, and AI and software engineering folks also brought their knowledge in a way to compete this competition, because the rule here is pretty simple: find the bugs and fixing it. Given these open competitions, what's interesting at the end, all these 7 teams who proceed to the final are mainly rooted in the security area. It means, or it implicates, that it's significantly important to leverage LLM by bringing your domain expertise. I think this is the best way to leverage AI in a way to solve what you are familiar with. So during the semi-final, we analyzed 5 different real-world applications, including Linux kernel and Nginx and Tika and Jenkins and SQLite. Again, these are the well-tested programs through all these traditional software techniques, as well as a pen tester who already look into those details. And given this well-tested program, we still be able to find those vulnerabilities by leveraging AI. So what are the challenges that we are talking in this competition? This is one of the exemplar that organizers share during the competition. This is one box in the Linux kernel. When 2 processes create a secure channel between them, one process send a session key to the other side, and this is the one that initiated those session key. So one process package everything in their packet, in the domain packet, send this packet to the receiver side in a way that they create a secure session. All this information is written in the packet that include the size of the data, the size of the key. Unfortunately here, if you see the last line of the code, they naively copy the entire of the key written in here inside the packet, instead of respecting the actual size of the packet. So that if you craft those informations inside the packet, you can trigger those vulnerability out of bound write as part of the main copy in the last line in the screen. Then how to find this vulnerability by LLM? Either you can ask LLM to this particular function to find those vulnerability, but there is a higher chance of identify them. But unfortunately, Linux has 30 million lines of code. But if you convert this into token usage, probably the factor of 10 or more. This humongous piles of token in the Linux repository. What is the right way to find those vulnerabilities? So in the competitions, we have to reach those vulnerabilities through a driver, sometimes known as a harness or fuzzing driver or fuzzing harness. So we are not just identifying those vulnerabilities. Our job is to creating the input that trigger the execution of the program in a way to reach those locations. In the context of the Linux kernel, there is a program, this user space program, that invoke a sequence of the system call in a way to drive the state of Linux kernel in a way that we can trigger those vulnerability. So that your job as a proof, you have to create those bug triggering input that is processed by user space, so that the user space program drive those state inside the kernel so that we can ultimately trigger those vulnerability. So this is what we call proof of vulnerability, because we have sanitization applied to the context of the Linux kernel. Whenever you trigger those symptoms, in this case out of bound, you can crash the program. Typically, we have nice mechanism as a judge to identify those states by install a sanitizer, such as other sanitizers or whatnot, in a way that we can universally identify those symptoms in the program. When we apply static techniques like LLM or CodeQL, there's so many false positive we create. For example, in this particular code snippet alone, if you run CodeQL against it, CodeQL will complain about those particular routine. In kmalloc, for example, the size of the kmalloc, the argument of the kmalloc is a size t parameter, which means it's depending on the architecture, just 32 and 64-bit architectures, all depends. But interestingly here, there's just 16 bits of information flow to the kmalloc. It smells bad because it likely causes an integer overflow associated with it in the later phase of the code because they're not explicitly encasing those operations when we pass this information to the kmalloc. But it's not it doesn't necessarily mean it's actually buggy. The bug exists in the other side of the implementation. It's not necessarily about the kmalloc. So the whole point of this competition is how to resolve this reachability problem by design, so that instead of asking you to spot those vulnerability, our job is to find those input that really reach those locations, so that we can evaluate the severity of those vulnerability, so that we can ultimately save time for security auditor when it comes to understanding those vulnerability in detail. This is well aligned with the AI slop argument from the community. So AI can generate all these reports, sometimes hallucinated, but whenever it generates the convincing report, it ended up wasting time in the security auditor, security researchers per se, so that the whole point of resolving reachability as part of the competition is to address those problems that we are facing in our community as well. So when Fuzzer says it's a bug, it's 100% true positive because there is a proof about sanitization report so that developer can just reproduce those vulnerability before even addressing them. So what type of security task we did as part of AICC? There are 4 different tasks we execute in 2 different modes. Of course, you have to find those proof of vulnerability that I described before, but you also have to fix those vulnerability that you found. Also, there is what we call task called Sheriff Assessment. So all these static analysis tools such as CodeQL emit those reports as part of Sheriff format, meaning that our job is given all this static report, our job is to evaluate the correctness of those reports so that we can report this bug is false positive or this bug is actually true positive in a way that we can ultimately save or triage those vulnerability reports from static tools as well. And last, bundling task is to connect those Sheriff report to the bugs that we found in a way that we can get extra score by connecting these 2 informations during the competition. We're gonna execute these 4 different security tests in 2 different modes. Our job is to scan entire of the source code. Sometimes organizers send a diff, meaning that your job is to actually execute these 4 different tasks associated with the diff, which probably the feature patch from the developer. You can think of those usage as part of the developer lifecycle. For example, whenever they create a new commit, our job is to perform those 4 security tasks more quickly with a smaller time budget on this PR, for example. The entire competitions was happened in last year's as part of the DEF CON in the stage. This is a visualization of competitions. Unfortunately, these autonomous systems, we expose the API, it only get the URL of the repository. The rest of the process is completely autonomous. So that you can see that in the middle, this represents the complexity of repository, so that everything is just green dot in terms of code graph. And then system is interacting with a LLM service which you represent as a purple box on the top. Our team won the competitions. As part of final round, we got about $4 million cash prize, including the semi-final donations. We got about $6 million. And after that, we actually execute this we actually do the real world bug bounty by using this system as it is, so that we ended up adding about $150,000 additional bonus out of this competition. We are so much proud, of course, because 2 years of hard work, finally it came to conclusion. But what we most proud of is not just we won the competition, we actually crushed every single category of those competitions as well. We scored overall 2 times of the rest of the team, rest of the winning team. And also we actually achieved highest score in correctness submissions, because all these AI slot can be addressed by those competitions as one part of the metric. So that when we submit those judgment call for sheriff report and the bug that we actually report to the systems with the patch, we have very high accuracy. So that we have almost 90% or more accuracies in terms of what we report to the organizer, so that we really respect the developer time out of the systems, that every single bug report that we are making are really worth investigating in detail by human auditor. In the semifinal, we analyzed about 28 open source repositories, that including curl and libxmls and systemd or whatnot. And as part of this competition, organizer injected about 53 vulnerability to this repository, 70 vulnerability to the repository, and about 50 of them are actually identified by all this team together, and majority of them are fixed on time. What's interesting here is that we are not just asked to find those synthetic vulnerability, we also have a freedom to find zero-day vulnerability in this repository. During the semifinal, we found a zero-day vulnerability in the SQLite. We are the only one who actually found those vulnerabilities by leveraging LLM. But in the final, in team total together, we found about 18 vulnerabilities. But what's interesting here is the amount of money that we actually spent together. In all the teams spent about $360,000 to perform those security tests. But if you divide those amount by the security tests that we perform, it's shockingly low, meaning that with the mere of $100, we can perform those security tests. Given unknown repository we never saw before, we can still execute those security tests. We can actually reveal those vulnerabilities with this small amount of money. That include the expenses in the cloud resources, and as well as LLM credit that we spend for security auditing. So if you compare with the human auditor, this is remarkably low, right? Then this is a big game-changing number that we have to understand as a security community. So I'd like to talk about our approach and how we actually win those competitions, what are the design decisions that we made as part of these competitions as well. You probably heard this remarkable achievement of LLM model. We heard that LLM achieved the reasoning capability of IMO competitions. So all professional math students now cannot compete with the LLM in commodity model that we have. Even for HoTSoS, the programming competition, already the commodity LLM already achieved the professional programming task in HoTSoS, so that they are simply doing better job with small amount of money. You also probably heard about Anthropic's new model, Mythos, and also part of the project Glassstream. They announced that now their reasoning model had a step jump in terms of security tests. I think this is what's happening right now. So that what about we ask this simple request to all these commodity LLM? What about we just create the prompt saying that, hey, what about you just write cyber reasoning system? It's a cyber reasoning system, it's an autonomous system that find and fix those vulnerabilities part of AICC. It's a pretty well-known concept to the community. So what about we ask each of those agents to write those CRS and really compete in DARPA AIxCC? So we have 7 working systems as open source. Then do we believe that all these AI systems can create and design these cyber reasoning systems as a level of the human written cyber reasoning system as part of DARPA AIxCC? Unfortunately, today's LLM has certain limitations. It's not AGI yet per se. They certainly have a capability, but unfortunately, the way they organize and tackle this high-level idea and still limited in certain sense, but we still see huge benefit of leveraging LLM in certain component of the security test that we like to resolve by leveraging LLM. But I truly believe tomorrow's LLM with much higher reasoning capability, with the longer timeline of execution, they're a surprising good right now, but still they can achieve those level of cyber reasoning systems that we can design right now. But talk today is all about, hey, how to overcome today's limitations, today's LLM's limitations in leveraging our security task as well. In certain sense, the current AICC texts are fundamentally hard, meaning that finding or fixing those vulnerabilities are still extremely hard, although it's well demonstrated by those AI companies, but we couldn't resolve all these CVE coming next month per se. Like all these AI companies say they found 500 vulnerable CVE, for example, but we're still gonna see more CVE next month as well. Meaning that there are certain part of the code bases that need serious look by human auditor in this current state, but we like to make those systems in a way that we can actually solve those security problems altogether. The one-line summary of our experience of interacting with LLM is that you probably know the Jack in Incredible. This is a baby, superhero baby born out of two hero parents. What's interesting here is that Jack has a superpower for sure. It can transform to any superhero skills. It can render those. Unfortunately, it's extremely hard to control. So our experience of handling this LLM is all about how to well babysit Jack. Sometimes we can say, we can encourage Jack, hey, you should be a security researcher, you're doing a great job. But at the same time, you have to threaten it. Hey, like you have to work hard, or you have to upset about how you perform. Sometimes you can give tip in a way that it actually performs. Unfortunately, this is an empirical science, so we have to approach LLM as a black box, because even if you understand all these details of the transformer work, how transformer work and how actually the model evolve, the technique of the fine-tuning doesn't necessarily help in terms of leveraging or unleash the capability of LLM model for security tests that we care. When we start those competition, we start as very much as skeptics. We rather want to demonstrate that how this traditional security tool can outcompete the LLM-driven teams per se. But for reasons, we evaluate all these latest LLM. Their performance was terrible 2 years ago. They're not usable per se. We have to talk about all these little details about prompting technique. Now we don't have to talk about prompting technique because of the advance happening in this LLM. But at the time, we have to talk about how to construct the chain of thought or tree of thought or self-consistency in a way that we can leverage the LLM in the right context, in the right way. Sometimes people discover lots of interesting tips, like tricks. For example, if you say we're gonna tip like $200, or we're gonna say tip $20, depending on the amount of tip, actually the amount of response token actually increases linearly. So that we have to figure it out what's the right way to formulate this context. And this is a kind of black science. We have to try all different insights that we have in a way to maximize the true capability of LLM by formulating those prompts as well. So many of these discussions are preliminary in a sense that, hey, what is the right way to ask to generate patch? Or what is the right way to display source code in a way that LLM can actually understand? Is it okay to create the line numbers as a prefix so that, hey, this is not necessarily well-structured AST. Does LLM really understand the relationship between line numbers and tokens? And what are all those? So sometimes LLM make tons of mistakes in AST, so that we have tons of pipeline to recover from those AST, so that we can fix those in a way that correctly patch those vulnerability. Or sometimes, hey, why not just asking LLM to just rewrite the entire functions, or sometimes ask it to fill in the middle instead of completing the rest of the code snippet. So all these techniques are rooted by the design of the LLM at the time, but now that we can see this increasing capability of the LLM, particularly when you're interacting with the CLI, all this scaffolding around actually got all these lessons that we've been exploring together as a community. We also observed the context window seems like fundamental problem, because when you're analyzing 100 million token of Linux kernel, you cannot just embed everything and ask. Unfortunately, whenever we see some of the race going on in increasing token window, but unfortunately though, even if you provide a million token, we still observe, depending on where we put the needle, the performance of finding those needle drastically different. So that it's similar to what we are interacting with baby Jack, right? If you provide more information to Jack, he got distracted by this such amount of information he had to handle, for example. So that still is valuable to leverage the given context window in the right way, so that we can fully leverage the potential of LLM in terms of finding those vulnerability and fixing it. There are some interesting characteristics in AI, generative AI, in terms of security tasks. Many people got excited about generative AI because the amount of the response token. For example, when we say, hey, can you create a new website? We're gonna now populate this website with 10,000s of lines of code pretty easily, which previously we thought we have to put human effort to write and construct those designs from scratch. But this is a huge help for most of the programmers who got excited about generative AI. But in terms of security tasks, the ratio is the opposite, meaning that we have pile of information that we like to process. It's not particularly generative AI. The generative AI component is about how to create the token of yes or no. So we can ask, hey, can you find the buggy line? Is it code snippet is buggy or not? How could you generate this, play against this one? Likely we have 100 lines of code emitting max in terms of writing exploitation, but these ratios is quite reversed. And most of the generative AI services optimize for the usage cases in the formal, but we like to leverage current AI in a way that we can maximize certain tasks in security, such as finding vulnerability or validating those findings by leveraging LLM. But we, as an AI, even though we started as an AI skeptic, we started seeing some of the potentials of leveraging AI as part of our program. We started seeing some of the framework, such as LangChain and Llama Index, for example, or Semantic Kernel from Microsoft. And these are amazing organizations how to address the limitations of LLM at the time, so that we start creating a notion of code interpretation, meaning that now it's common, very common that LLM, instead of just answering those questions, it solved the questions by creating the code snippet. It was breakthrough concept because many people at the time just focused on the response as a text, but now we have additional component we implemented as in a way that we can generate the Python code as part of the communication, so that we can actually solve the questions that we like to solve, so that we can increasing the expressiveness of the LLM, not just limited by the language behind. Not only that, we also introduced the notion of the function call. At that time, no one actually implemented this function call, so that we have a universal layer, the XML-based function call that we observe through the output in a way that we can enable this loop of the function call and return as a tool call as part of our systems at the time. One of the breakthrough happened at the time, what we call software engineering agent. You probably heard some breakthrough in the OpenDevin or SWE agents, which are still popular right now. But at the time, is a basic form of the AGI. We observe those usage cases of CLI are well deserved, so that we got excited about those opportunities. So many of our patch generation is actually based on software engineering agent and ADAR as a backend. But we extend those toolset extensively, but these are the things that we like to take advantage of the community, so that if LLM capability increase, this scaffolding still stay the same, but still improve the quality of those output of software engineering tasks. As said before, because we started as AI skeptics, in semifinal, we didn't leverage LLM that much. Unless for the security patch generations, we heavily rely on LLM. But in terms of finding bugs, we start augmenting LLM in very small component of fudging loop as a human. For example, before launching the entire fudging process, we leverage the LLM in a way to create a seed so that we can bootstrap this fudging process quicker. So that whole proposal of this competition, again, how to improve the traditional vulnerability scanner that we already have, such as fudgings and static tools that we create, such as concurrent executions or symbolic execution. But we improve those traditional software stack by leveraging LLM. Because in the semifinal, we have a small amount of budget for the competitions as well. But after semifinal competition, everything changed. For example, now context window doesn't seem to be a problematic anymore because we start seeing lots of interesting techniques. For example, we can now compact the history in the right way, in the right time. Not only that, we have many of architecture changes. For example, instead of just leveraging entire context window as one session, you can forward the sessions as a sub-agents, or you can even create the multiple agents that have sole interest in solving a one simple task. So that instead of wasting or sharing those contexts among sub-agents, we can solve those tasks by combining them all together. So by combining all these techniques, we now see huge opportunity of leveraging context, even if the context window is just small, we can leverage those context windows in the right time and right way so that we are not suffering from the limitations of context window anymore. Although we start seeing the increasing number of context window by Gemini, and now HoTSoS provide the million context window, but we still leverage the small amount of context window for the competitions at the time. I think these lessons is still true in today's LLM as well. We also see some of the revolutions happen driven by LLM company. Now, all these LLM company has a scaffolding for their own model, such as Cloud and Gemini, even Codex for OpenAI model. We also see GitHub's Copilot now have CLI that can redirect all these model-based completions depending on the user's request as well. So we actually reverse engineer all these implementations of Code Cloud and Codex and whatnot. Like, although now the code basis of the Cloud Code is leaked so that everyone can see what's actually implemented, but we got whole lessons by reverse engineering those model in a way that we can implement the state-of-the-art architectures of the agent, but we put those model as one of the small component in our patching agent, which I'm gonna describe later on. When we are preparing for the final, we leverage the LLM in every single component of our systems, what we call Atlantis. We have a universal LLM proxy layer that we're not just launching a one agent, we actually launch agent, the exact same implementation by switching the multiple model so that we can leverage diversity of those model. We've been saying that this is a way to leverage the creativity of the model. When you do static analysis, we actually saturate the amount. Once you run the static analysis, mostly likely the output is final, meaning that this is everything that we can do by leveraging the static analysis. But when you're leveraging LLM, there's a more chance that you're going to discover something interesting. But as far as you can making, if you make the other process of validating those reports from the LLM quick enough, then it's completely fine. LLM hallucinates sometime, but the amount of penalty that we have of validating those input is very quick, so that we promote those diversity and creativity LLM in a way that we can maximize the amount of hit rate of the true positive in terms of hitting sanitization as part of these competitions as well. We have a multiple component. While in the bug finding module, we took the idea of n-versioning in a way that we implement multiple versions of the CRS in a way that we can leverage those diversities as part of the bug finding, which I'm gonna describe later. In terms of patching, we also took the idea of ensembling. Similar to the diversity of the model, we develop all these small agents in a way that we can maximize throughput when we combine all the agents that we develop together. Let me highlight some of the design decisions we made for each of those components. In terms of bug finding CRS, we took the idea of n-versioning, not just for leveraging the diversity of the model. We also want to leverage the idea of fault tolerance. Because the system should be run completely autonomous for a week for the competitions, our system designed to be very robust. We might see some of actually during the competition, we actually saw many of anomaly in terms of building process because we have to instrument a lot of in order to enable these symbolic executions and whatnot, we have to instrument quite a lot in terms of building process, which means it's very fragile whenever we meet the buggy building scripts. We have to recover from them. Sometimes organizer make mistakes in how to build the process, then LLM component in our systems sometimes fail, but we have to make sure the entire system is actually up and running or recover from those mistakes that we make during the systems. So we design n-versioning as a way to recover or make entire system robust. In fact, we observe actually some of the failure during the competition. Our system successfully recovered from those because of n-versioning design that we took. We intentionally divide the team in a way that we minimize the shared component, but we promote their research in every aspect of what they're doing, so that we have a specialized team who just design for CRS for C challenges. We have a team that work on Java side, and there's a team that work for language agnostic manner. So each of those components are activated in the right context in a way that we can have at least two components running concurrently in terms of finding bugs for such challenges in C and Java at least. For C and Java, we didn't simply give up all these traditional tools. We improve a lot of traditional analysis tool such as fuzzing by providing ensembling mechanisms depending on the resource usage and progress at a time. We can select those fuzzing in the right context as well. In terms of concurrent execution, we implemented in-house versions of concurrent execution for Java as well, which we spent ridiculous amount of engineering effort in a way that still we perform this traditional analysis while extending our system to leverage the LLM, which I'm going to describe later on as well. For C and Java, we also implemented directive version because we see some of the interesting use cases of validating sheriff report. Say, when we get this sheriff report for validations, we drive the entire execution of the fuzzer to identify those locations. Basically, find the input that trigger those vulnerability in the right spot in a way that we can quickly validate those sheriff report. You can think of this way, because through the instrumentations that we made during the compilation process, we have a distance metrics as a gradient in a way that we can gradually push those direction from input mutation to the locations that we'd like to hit during the fuzzing process. I can provide a little bit of comparison between all these components. For example, when we are designing C specialized agents, we take a risk of instrumenting heavily so that we replace the default fuzzing engine through libfl because the organizer provides the harness through the libfuzzer as a default engine that was supported by OSS Fuzz project, but we like to improve those by leveraging the architecture of libfl with the various notions of implementations and coverage and instrumentations and whatnot as well. So we have a higher chance, but in terms of Atlanta multiline, we avoid those instrumentation. We took the idea of fuzzing libfuzzer as an implementator, but we extend the libfuzzer by providing all these shared plugin that libfuzzer is aware of. For example, we tap into the instrumentations, we tap into the input generation, for example, in a way that we can provide additional capability as part of the diffuser framework, so that we can minimize the failure of instrumentations that we observe during the competitions as well. So in terms of CCRS, we leverage the LLM in certain component that we believe is useful, but in terms of multi-lang, we heavily rely on LLM so that we can do even code graph generations. We have a static component, the agent that statically explore the code bases to identify the buggy location in a way that all these direct diffuser just shooting for those locations that we identify as well. Even for the resource allocations, Atlanta C took the idea of time-based resource allocations so that whenever you see some of the increase of the coverage, we can put more resources in those fuzzing harness. If we recognize a fuzzing harness that never reach those locations that we are interested in, we even disable them. Because during the competition, you have a list of the harness, sometimes like 20 or even 100 of a harness you have to schedule together in terms of find bugs. But multi-lang cases, we still respect those chances in a way that we allocate the resources uniformly across the harness that we have to find bugs against. There are many interesting characteristics in terms of buzzing and LLM, which I describe as a ratio between the prompt and response, which is very important. But at the same time, there's a performance characteristic differences as well. LLM response time is extremely slow. You cannot just embarrassingly increase the amount of parallelism in terms of execution, because all this commodity LLM provider has a threshold, meaning that you cannot go beyond 10 requests per second per services. But if you multiply by 4 or 5, depending on the services that you're using, you cannot go beyond 100 requests per second. But interestingly, in the fuzzing side, we have capability of running 5,000 requests per second, so that if you multiply by 60,000 virtual core that we are leveraging in the cloud spaces, we have ridiculous amount of parallelism going on, so that we can leverage the CPU resources in a way to validate those findings. So even if you made a mistake in the LLM side, it still doesn't cause much, because most of the fuzzing routine is a way to increase the coverage, not hitting the bugs. So that whenever we make the mistake in the other pipeline, we still completely fine in terms of hitting this amount of rate in the fuzzing side as well. And in the fuzzing, there's no false positive, but in LLM, there are tons of false positive it creates because of hallucinations and maybe missing context around. So that, but we still leverage the fuzzing in a way that we can resolve those false positive from LLM side. And this every decision we made in those settings is only possible because of the existence of Oracle. The Oracle as sanitizers in fuzzing, basically you create some judge in a way to identify the symptomatic state in the program, which is crashing of the program. So we can identify those crash, we can catch those crash more systematically, although we don't know existence of the vulnerability, but we can tell this abnormalous state of the program by installing the sanitizers in the C program. This is a beautiful property that we leverage during the competition, because this is similar to what Alpha Evolve in the Google leveraging in terms of designing their systems. The system now have a judge in a way that we can evolve the entire pipeline during the competitions as well. I like to highlight some of the design decision, some of the components that we designed for C, Atlanta C version tailored for C programming languages. Again, you can ask LLM to create the input, which is a beautiful property, but at the same time, you can ask LLM to express what you want to test against the fuzzer, so that it express the certain input coverage that the LLM like to explore in form of Python code, so that we provide all this utility in a way that LLM just invoke those Python API in a way that they can express not just one concrete input that we can test against the fuzzer instance, but now LLM express the strategy of input mutation that can cover the one of the instance that can hit the symptomatic behavior of the program. So we have a much higher throughput because we have much higher hit rate by having by covering those input state that LLM considering point, so that we now have LLM generate the input mutator and input mutator run as part of the fudging process, so that we have a higher chance of hitting those vulnerability LLM care about. Also, in terms of concurrent execution, we also leverage the LLM. So typical failure of concurrent executions is whenever we meet some of the environment that we don't have model. For example, if we invoke a system call, this is now user space to kernel transition, and likely we don't have proper model of the kernel because this is not what we instrumented during the instrumentation process for concurrent execution. But whenever we meet those, we invoke the LLM in a way to construct, at least estimate the representation of constraint for those symbolic execution in terms of symbolic execution, so that we can still continue to execute after. Although it makes tons of mistakes, but it's completely fine because the penalty of incorrect model of concurrent execution for us is extremely low. So that is completely fine. It's more important to actually complete the execution of concurrent execution so that we have a certain candidate that we can validate after the execution, instead of just discarding this concurrent execution with error in bug finding. Not only that, we leverage LLM interesting way to make this concurrent execution possible in language agnostic way. So instead of instrumenting code executing these symbolic executions one by one, you can construct the constraint by asking LLM to generate the constraint for every single line that we are executing. Say this is a line that we are executing, you can ask LLM, hey, could you create a constraint per statement inside the C program, for example, so that we can construct some of language agnostic concurrent execute on top of LLM. In terms of fudging, we extend fudging in heavily across the pipeline. Typical fudging is language specific. For example, this is common workflow of the fudging. It has a scheduling phase in a way the evaluating state and pick the corresponding input state, and we perform the implementations that we actually run. We get the feedback. Every single phase is very language specific, but in order to implement this in the language agnostic way, we replace many of the language specific one by leveraging LLM. This is what we call Atlantis multi-line. Many of those components heavily rely on LLM in a way that we can abstract the language-specific component in a way that our agent can still run against the new code bases that we observe. We have a component for input reverser, which is drastically improve the performance of the fudging's implementation. Most of the fudging happen treat the input as a simple byte or plain byte, so that they can mutate one byte at a time in a way that we can observe coverage changes across the fudging pipeline. But if you have a better idea of what are the type of program or structure of the input, in a way that say this is the actual field, so that instead of just modifying a one particular byte, what about we modify this length of field in the structure and corresponding byte, or we can avoid some of the contents of the input in a way that we can just focus on the metadata, which has a significant impact in terms of code execution, so that we have pipeline to recognize those states in a way that we can improve the quality of the implementations as well. We even create the language that describe or the input structure with the uncertainty, so that although because LLM make all these mistakes all the time, so that we have probabilistic notions of the input state, so that we take the opinion of LLM in terms of implementations, not heavily rely on LLM's structure that is emitting. So we take advantage of high-level idea that, hey, in the zip file, zip format, there is a XML inside. Then we focus on the implementations on the content that actually matter, not the input format of the zip, for example. This LLM opinionated approach actually work pretty well in those contexts in terms of what type of implementations we have to do as well. We also create the dictionary based on all these document behind the repository. You can search it through the test cases and documentations in a way that we can think about how to test this program. So LLM explore all these locations and create the final dictionary format, so that instead of just modifying one byte at a time, we now swap those or entry by leveraging the AFL's dictionary format that all these fuzzy understand as well. We also have an agentic agent that statically explore those code locations, starting from constructing the code graph and identify the locations that they believe is buggy. And also we emit the precondition how to reach those locations as a sequence of list in a way that other agent can resolve those inputs based the constraint one at a time, so that we can ultimately reach those locations to hit those vulnerability in a pure LLM way as well. In terms of patching, we took the idea of ensemble, meaning that we intentionally break the design spaces and architecture choices across those agents that we develop. We implement 6 to 7 agents that independently explore those patch generation, because similar to the sanitization, we have a very strong oracle in patching, meaning that given a bug triggering input, we can always validate whether our patch prevent those vulnerabilities that we discover as a guideline. So because of this judge existence, so that we can leverage our design focus on leveraging diversity of the LLM and model and architecture in a way that we can actually fix those vulnerability. We implement 6 different architecture, or 7, including custom model. So we have intentionally picked various architecture choices and model behind. So some of the example is that what we call Martin. This is another interesting choice we made for this particular agent. It has a very deterministic workflow, but we provide complex tool call. For example, we provide simple lookup and stack recovery as a tool, or we can even do reverse execution starting from the crashing location, so that we can recover the stack frame for the root cause analysis. But once we do these 4 localizations as one agent, we can just generate the patch. In fact, it turns out generating patch with the proper root cause analysis is extremely easy, so that we can simplify this entire workflow, but we focus on providing more complex tool that agent can leverage. But we have other extreme spectrum that have very complex workflow with a very simplistic tool as well. In terms of sub-agent, we, in order to save the context window, we create the sub-agent for various tests that we define, such as root cause analysis and also handling or recovery of the stack frame. Now everything works in terms of sub-agent. We also have a team of agent as a multi-agent approach, so that the patching agent, evaluation agent, and analysis agent share some common knowledge base, and they debate about how to actually create the patch in the right way. And evaluation agent always provide the evaluation result and provide the perspective of evaluator in a way that we can create the semantically correct patch at the end as a group as well. This ensemble approach worked extremely well. If we couldn't achieve every single benchmark by having one single agent, but if you ensemble all them together, we actually achieve 100% for all the benchmark that we created. And this also provides another advantages of creating those agents, or like many of the agents are small, and we don't need much collaborations among team members. And if someone have idea that they can play with, they can create the new agent and plug into our system and see if it can identify some of the unique vulnerability that other agent couldn't find. You can design one agent can do very well across all different vulnerability, but that's not our goal. Our goal is to create one single agent can accelerate the performance in certain type. Then that's the criteria that we're going to accept as part of the ensembling approach that we take. Because if you can fix those vulnerabilities that other agent can fix, it doesn't create the value as a team. So that we have tons of small agents. After all these criteria and evaluation, we ended up having 6 or 7 at the end for the final competition. We found many zero-day vulnerability, including SQLite. For the final, we found about 6 new zero-day vulnerability that is not known to the developer. In fact, we actually demonstrate exploitations of, I would say, SQLite as well, so that we can actually trigger those vulnerability, and we provide the POC in a way that we can communicate all these developers to fix them. After AICC, we had another chance to run AICC develop artifact against open source project. We did some of the bug finding campaign for 2 weeks. In our hackathon, we actually find about 17 to 20 vulnerability, so that we got extra $170,000 as bug bounty because of those campaigns that we did against all these high-profile software like Memcached and PHP and whatnot. So what's next? Our team's implementations is selected as a Linux Foundation's official project, so that is supported by OpenSSF, so that we officially become part of OpenSSF project, so that we create a new open source project called HoTSoS CRS that can abstract and support all these existing CRS implementation from AICC. So previously, AICC implementation is very specific to the competition environment because it requires ridiculous amount of cloud resources and ridiculous amount of LLM resources for the competition. But now you can launch within your single laptop or workstations or even cloud environment by leveraging HoTSoS CRS format. And now we provide 6 different implementations of all these architectures, including the commodity model backend CLI as well, so that you can do some of the evaluation by using HoTSoS CRS. And as far as you can provide the resource limit and API key, then our system can orchestrate the installations and running of entire of the CRS implementations in a single laptop. So we create the CRS benchmark in a way that all the cyber reasoning system can be evaluated. The many of the AI-driven approaches like Cloud Code and Cloud Codex and whatnot, they are focusing too much on the static side. But there are huge needs in the dynamic testing as well. So CRS benchmark try to address those 2 concerns at the same time, so that one can evaluate in the pure static way, one can evaluate by leveraging the fuzzing as a core means, for example. We truly believe it's time for real-world AIxCC. That's why we joined Microsoft. 6 other team members joined Microsoft and GitHub in a way that we can enable those capability to internal code bases at Microsoft and GitHub for the external repository they're hosted inside this platform for easy to use of those CRS implementations that we have. Other members also started the company, what we call QED auditing. They brought those AICC artifacts in financial institute in a way that they can provide those auditing, AI-backed auditing for blockchains and smart contracts and future financial institute and their infrastructures as well. They already found significant vulnerability. For example, they demonstrate a vulnerability that actually store $600 million in the testnet. So that they got huge bug bounty as a team, and also they now have a few customers that can provide AI-based auditing for every single PR that they generate as well. We open source everything. You can take a look and the details of implementations. Not only that, you can actually check the design report. It's 150 pages of design report, but we also summarize how other people actually did, so that you can explore all these design spaces of the CRS as part of this archive paper that we wrote a few weeks ago, so that you can take a look on those. And we truly believe this is not hype anymore. This is a true revolution happening in the AI space, so that many of the security tests can be done more effectively by leveraging LLM. Particularly if you combine this LLM technique with the traditional tool that our community has been building last decades, now have opportunity to find many of those vulnerability and address those vulnerability in short period of time, so that we can respond to the LLM equipped adversary as well. Thank you so much.